Chapter 4.4, Introduction to Trigonometric Equations. In the last lesson, you solved basic first-degree trigonometric equations over a restricted domain. Example, solve the equation sine theta equals 1/2 over the domain 0 degrees is less than or equal to theta is less than or equal to 360. Our domain tells us that if we use our calculator, we want it in degree mode, and also our answers will be in degrees. Sine theta equals 1/2. In the unit circle, sine is the y value, so this is saying y equals 1/2. We should recall that 1/2 is one of the side lengths in our 30, 60, 90 special triangle. I can draw the 30, 60, 90 special triangle. 90 degrees, 60 degrees, 30 degrees. The hypotenuse started as 2, but we divided it by 2 to get 1 for the unit circle. The bottom started as a 1, but we divided by 2. And the third side started as √3, and we divided it by 2. So which angle would give us sine theta equals 1/2? Sine is opposite over hypotenuse, so we want the opposite side to be 1/2. Then we would have to go from angle 30. That would give us opposite, and then over hypotenuse would be 1. So then we know that sine 30 degrees equals 1/2. But there could be more than one solution. Let's draw a diagram. Our domain is one full positive rotation. We have sine theta equals 1/2, so sine is positive. We use the cast rule, C-A-S-T. Where is sine positive? In quadrant 1 and in quadrant 2. So we can have a reference angle of 30 degrees, or we can just go, we know that the y value is 1/2. So we mark 1/2 and then draw over to the unit circle, put a dot in quadrant 1 and join that to the origin. Same thing in quadrant 2, go over to the unit circle at y equals 1/2, join that to the origin, and there's an image of our two angles. In quadrant 1, we know that theta r is 30 from our special triangle, 30 degrees. So quadrant 1, the angle would be 30 degrees. And then we have a second angle in quadrant 2 that we want to calculate. When calculating an angle in quadrant 2, we start with 180 degrees, which is all of quadrant 1 and quadrant 2, and then we subtract our reference angle, theta r, which in this case is 180 degrees minus 30 degrees, which then gives us theta equals 150 degrees, and we also have our theta equals 30 degrees. Now solve the same equation over the domain 0 is less than or equal to theta is less than or equal to 720. The first one was one full rotation around. This one, 720, is 360 times 2, so that's 2 full rotations. Let's draw a diagram. Y equals to 1/2. We know that our solutions are still in quadrants 1 and quadrants 2 because sine has to be positive 1/2. So we have our first angle, which was 30. We have our second angle, which was 150. Then if we go all the way around and back to our first angle, that would be another angle. And if we go all the way around and back to our second angle, that would be a fourth solution. So we have 4 thetas here. To find the other 2 angles, we go a full rotation, 360 degrees, and then we go to our first angle, which was 30 degrees. So that gets us to 390 degrees. For our second one, same thing, we go a full rotation, 360 degrees, and then we go to our second angle, which was 150, which gets us to 510 degrees. Then our solutions are theta equals 30 degrees, theta equals 150 degrees, theta equals 390 degrees, and theta equals 510 degrees. Recall, to write a general solution, we use p plus or minus 360 degrees n, where n is an element of I. That should actually really just say plus, because since we have integers, if we put a negative number in for the n, then we would be essentially subtracting. So really that should say plus. Hopefully it's edited once you get the notes. For the equation above, the general solution is theta equals 30 degrees plus, we'll get rid of the minus. It's not wrong if you have the minus, it's just redundant. You don't need that information. So 30 degrees plus 360 degrees times n. That would give us all of the 30-degree angles, so going around 1 full rotation and then 30 degrees, going around 2 full rotations and then 30 degrees, etc. And also our other solution would be 150 degrees plus 360 degrees n, where n is an element of I. So that would be all the rotations that go to 150 degrees after 1 full rotation or 2 full rotations or 3 full rotations. Then in radian measure, we can write theta equals pi over 6 plus 2 pi n, and also 5 pi over 6 plus 2 pi n, where n is an element of the integers. And then a note here in terms of how we write the domain for theta. We can write theta is an element of bracket 0, comma pi. This is the same as 0 is less than theta is less than pi. So rounded brackets mean we don't include the endpoints, but we include everything in between them. Or if we write theta is an element of square bracket 0, comma pi round bracket, this is like saying 0 is less than or equal to theta, which is less than pi. So square bracket means we're including the 0, round bracket means we're not including the pi. To solve trigonometric equations, we use the same rules that apply to other equations, but our goal is to isolate the trig function. Example, solve each trigonometric equation in the specified domain. 3 cos theta minus 1 equals cos theta plus 1 for the domain negative 2 pi is less than or equal to theta is less than or equal to 2 pi. So that'd be 1 full negative rotation and 1 full positive rotation. So just think of cos theta as x. We have 3x minus 1 equals x plus 1. If we were to solve this, we would want to group the x's together on one side and the non-x's together on the other side. So same thing, we're just saying our x is now cos theta. So let's add 1 to both sides. Then we get 3 cos theta equals cos theta plus 2. Let's subtract cos from the right side. Then we get 3 cos theta minus 1 cos theta is 2 cos theta equals 2. Then divide by 2, and we get cos theta equals 1. In the unit circle, remember cos is the x value. So this tells us that x equals 1. Let's draw a diagram of our unit circle. Where is x equal to positive 1? That would be this spot here. X is 1, y is 0. And then our domain is 1 full rotation in the negative direction and 1 full rotation in the positive direction. So first of all, we have an angle measure of 0 radians. Then if we go the negative direction, we would have negative 2 pi. And if we go from 0 positive direction back to our point, we get positive 2 pi. So our solutions for this trigonometric equation under this domain are theta equals negative 2 pi, 0, and 2 pi. For secant x plus 8 equals 0, for a domain of 0 degrees is less than or equal to theta is less than 360 degrees. Saying secant x is the same as secant theta, I'm going to change it to theta. Doesn't matter what we call it. It's like any variable. You can call it anything. So I'm going to change that to secant theta. Same idea. It's a linear. So I want to isolate my trig function. I'm going to subtract 8 from both sides. I get 4 secant theta equals negative 8. Then divide by 4. Secant theta equals negative 2. Secant theta is 1 over cos theta, which equals negative 2. Then cos theta, if I flip this around, negative 2 over 1, flip that around, we get cos theta is negative 1/2. And we know that in the unit circle, cos is the x value, so this tells us that x equals negative 1/2. So you can see why I decided to change my x, secant x, to a theta, because otherwise it might be confusing if I have cos x equals negative 1/2 and then I said x equals negative 1/2, because the angle does not equal negative 1/2. What I'm saying here is that on the unit circle, the x value represents the value of cos theta. Let's write a little note here about that. We changed the x in secant x to theta so we don't have two x's that represent different things. So we had secant x, where x represents an angle, and then we have cos theta, which is an x value on the unit circle. So let's draw a diagram. Cos theta is a negative value using the cast rule, C-A-S-T. That means our solutions have to be in quadrants 3 and 4. The x value is equal to negative 1/2. So there, go up until we meet the unit circle. We'll have a terminal arm here. And go down until we meet the unit circle. We'll have another terminal arm here. Our domain goes from 0 to 360, but not including 360. So we can have a full rotation and then stop right at 360, but not include that, which means we have two angles. We have this angle here and this angle here. We need to figure out the reference angle. I should recognize that 1/2 is a side measure in the 30, 60, 90 special triangle. I can draw that. 60 degrees at the bottom, 30 degrees at the top, 90 degrees at the bottom right. Our hypotenuse started as 2, but we divide by 2 for the unit circle, so we get a radius of 1. The bottom side started as 1, but we divide by 2 to get 1/2. And then the other side starts as √3, but we divide by 2. Cos is adjacent over hypotenuse, so which angle has 1/2 as the adjacent side? That would be angle 60. So our reference angle, theta r, is 60 degrees. Then our first angle, theta, would equal 180 degrees minus our reference angle, which gives us 120 degrees. And our second angle, we're in quadrant 3, so it'd be 180 degrees plus our reference angle, which is 240 degrees. And then just at the very end, remember we started with secant x and we changed it to secant theta. So really our solutions, instead of being written theta equals, should actually be written x equals. So we'd write x equals 120 degrees and x equals 240 degrees. Change theta back to x for solutions. Determine the general solution to 2 cos x minus square root 2 equals 0. Again, we can change this x to theta for the time being. We want to isolate cos theta, so we're going to add root 2 to both sides. Then we get 2 cos theta equals root 2. Divide by 2, and we get cos theta equals root 2 over 2. Then we should recognize that this is from our 45, 45, 90 triangle, which if you write in radians is pi over 4, pi over 4, pi over 2. When we're using this triangle, we don't need to draw the triangle because we know our reference angle has to be 45 degrees or pi over 4, since there's not two different acute triangles. So then theta r is pi over 4. Let's go to the top and draw a diagram. Check out the cast rule. Our cos theta is positive, so our solutions need to be in quadrants 1 and quadrant 4. Our reference angle is pi over 4, so our terminal arm will be halfway between the x and y axes in these two quadrants. Then our first principal angle would be pi over 4. And our second principal angle, theta, would equal, it's pi over 4 less than a full rotation, so 2 pi minus pi over 4. 2 pi can be written as 8 pi over 4 minus pi over 4, which gives 7 pi over 4. So these would be the two solutions in one full rotation, but we want a general solution, which means if we could continue rotating as many times as we want in the positive and in the negative direction. So our solution, we're going to change our theta back to x. We get x equals, our first angle is pi over 4 plus 2 pi n. Our second angle is 7 pi over 4 plus 2 pi n. So that's saying for the first one, we can go pi over 4 and then we can go another full rotation and another full rotation. And we're always going to get back to that point by doing full rotation. And a full rotation is 2 pi. So 2 pi times 1 gives us 1 full rotation. 2 pi times 3 gives us 3 full rotations. And we're just adding full rotations to our principal angle of pi over 4. And then same idea with our second angle, 7 pi over 4. We're going to 7 pi over 4. Then we're adding a full rotation to get back to that. And we're adding another full rotation, or going in the negative direction, adding a full rotation, etc., etc. And then we need to state that for these, we have that n is an element of the integers. So there's our general solution. Solve the equation square root 3 tan theta plus 1 equals 0 for the following. A domain of 0 less than equal to theta less than equal to 2 pi for the first one. Let's isolate tan theta here, subtract 1. We get square root 3 tan theta is negative 1. Divide by root 3. We get tan theta is negative 1 over square root 3. I should recognize that square root 3 is in my 30, 60, 90 special triangle. I can draw that triangle. "60 degrees bottom left, 90 degrees bottom right, 30 degrees at the top. Hypotenuse started as 2, we divide it by 2 to get 1. Bottom started as 1, we divide it by 2. And the other side started as root 3, and we divide it by 2. We need to figure out which angle is our reference angle. Is it 30 degrees or is it 60 degrees? So we can take the tan of both angles and see which one gives us 1 over root 3. I can start with looking from 60 degrees. Tan is opposite over adjacent, so tan of 60 degrees would equal, the opposite side here would be root 3 over 2. The adjacent side would be 1/2. So root 3 over 2 divided by 1/2. When we divide by fractions, we multiply by the reciprocal. So root 3 over 2 times 2 over 1. And our 2's divide to 1, and we get root 3 over 1. Is that the same as our answer? No, we had tan theta is negative 1 over root 3. So it can't be tan 60, it's got to be tan 30. Let's just double check. Tan 30 degrees equals, opposite from 30 would be 1/2. And then divided by the adjacent side would be root 3 over 2. We multiply by the reciprocal of the second fraction, so 1/2 times 2 over root 3. Our 2's divide out, and we get 1 over root 3. So our reference angle, theta r equals 30 degrees, which is pi over 6. Let's draw a diagram. Cast rule. We have tan is negative 1 over root 3, so tan negative would be quadrant 2 and quadrant 4. Our reference angle is pi over 6, which is the smallest of our special angles. So about here and here, we'll say. Then we have our domain is from 0 less than equal to theta less than equal to 2 pi. So one full rotation in the positive direction, which means we have one angle here and one angle here, and that's it. So we're going to have two solutions. The first one, theta would equal pi, because that is quadrants 1 and quadrants 2, and then minus our reference angle of pi over 6. We can write pi as 6 pi over 6, and then minus pi over 6. So we get theta equals 5 pi over 6. Then our second angle in quadrant 4, theta equals a full rotation, 2 pi, minus our reference angle, pi over 6. 2 pi can be written as 12 pi over 6 minus pi over 6. Then theta equals 11 pi over 6. So our two solutions are theta equals 5 pi over 6 and theta equals 11 pi over 6. And then B, do the same thing, but our domain is now negative pi less than equal to theta less than equal to 3 pi. Let's draw our diagram. We still have tan is negative, so our solutions have to be in quadrants 2 and 4. We still have a reference angle of pi over 6. So our terminal arms are in the same locations. The only thing that's different is now we can go negative pi. So if we go the negative direction, we would have this angle. We get to pi, there's no other angle. So we have one negative angle, and that would be theta equals negative our reference angle, pi over 6. And then we can go 3 pi in the positive direction, so that would be a full rotation, which has 2 solutions, as we already saw, and then another half rotation, which has another 1 solution. So we already have 5 pi over 6 and 11 pi over 6, but if we go around 1 full rotation and then get back to this angle, and that angle would be a full rotation, theta equals 2 pi, plus the measure of this angle, which was 5 pi over 6. 2 pi can be written as 12 pi over 6 plus 5 pi over 6. So then theta would equal 17 pi over 6. And then we also have the 2 original angles here and here. So we have 4 solutions for this domain, which are theta equals negative pi over 6, 5 pi over 6, 11 pi over 6, and our biggest one is 17 pi over 6. And then part C wants the general solution. We have 2 principal angles here, but if we look at our principal angles, we should notice something about them. We have one here, one in quadrant 4, one in quadrant 2. if you notice, they're actually pi away from each other. So we can write this with one solution instead of up here where we had to write pi over 4 plus 2 pi n and 7 pi over 4 plus 2 pi n. And that's because they're not pi away from each other, so we have to write them separately. But since in this one they are pi away from each other, we can write our general solution with one angle as theta equals our smallest positive angle, which was 5 pi over 6. And then plus, instead of 2 pi n, we're not going a full rotation, we're now going to go half a rotation. So we're going to go pi to get to the next one. So instead of 2 pi n, we put pi n, where n is an element of the integers. So if n is 0, we get to 5 pi over 6, which is here. If n is 1, we would add pi, so we would get to our second angle, which was 11 pi over 6. If we add pi again, we get back to this one, add pi again, and so on and so on. And same with going the negative direction. Solve the equation sine x equals -4 over 7 over the domain 0 is less than theta is less than 2 pi to the nearest tenth of a radian using a graphical method. Graphical method, this tells us we can use our graphing calculator. And the domain being between 0 and 2 pi tells us we need to be in radian mode. Just like solving any equation graphically, there's two ways we can do it. We have sine x is -4 over 7. We could move everything to one side of the equation so that the other side equals 0, and then solve for the x-intercepts, or we can graph two separate equations and find the x values of the intersection points. I'm going to do it that way. y1 equals sine x, and y2 is -4 over 7. Find the y values of the intersection points. We need to check the mode. We want it in radians. Mine is in radians, so I'm good to go. Go to y equals, enter our equations, which are sine x, and then the second one is fraction -4 over 7. Graph that, and with a standard window, we get this image. We want to restrict our domain to be what's listed here, which is 0 is less than theta is less than 2 pi. So I'm going to go to my window and I'm going to change my x minimum to 0, the lowest value of the domain, and my x maximum to 2 pi, 2, second function pi, enter. And then in this case, it doesn't really matter what we count up by because we're rounding to the nearest tenth either way. But we can get in the habit of, for the x-axis, counting up by one of our special angles. So pi over 6, pi over 4, pi over 3, one of those. I'm going to go with pi over 6 because that's my smallest of the special angles. And then my y value, if I think about the sine function on the unit circle, the biggest value that I ever have for y is 1, and that's when x equals to 0. So I'm going to put my y min just to even something small. Let's say -2 and +2 for the y max, and I can count up by ones. That sounds good. There we go. So I have a nice zoomed in image of my graph over the domain of 0 to 2 pi. Let's draw a quick sketch here. I have y is 1, and then y is 2, y is -1, and then y is -2. The line y equals -4/7, that's a little bit smaller of a number than -0.5, so that's approximately here. And then the curvy line, that's our sine function. It looks like it's got an x-intercept at 0, 0, and then right at the end of our domain at 2 pi, and then in the middle as well. We're just doing a rough sketch here. And then it looks like in between each x-intercept, on the two left x-intercepts, it goes up to a max of 1 in between those, and in between the next two, it goes down to a minimum of -1. So it looks roughly like this. And then we see that we have two intersection points, one here and one here. That's the information that we're interested in. So we do second trace number 5. For the first one, just hit enter, enter, enter on a TI, and we get x equals, we don't care about the y value because we know it's just going to be at -4/7. Care about the x value, so it is 3.749, and then we do the same thing, second trace number 5 again. This time move your cursor closer to the point you're trying to find before you hit enter on the first curve, and then do the same thing on the second curve. Move it closer to the point you're trying to find, hit enter, and then hit enter again. And it tells us the x value for this intersection point is x equals 5.676. So our solutions, we want to round to the 10th place. We have x equals 3.7 and x equals 5.7. And let's just make a note here on what we had our window settings for this graph. The x-min was the low end of the domain, which was 0. The x-max was the high end of the domain, which was 2 pi. The x-scale, we went up by pi/6. Then the y-min was -2. The y-max was 2, and the y-scale was 1. Solving second-degree trigonometric equations. Recall the process for solving second-degree algebraic equations. First, we set the equation equal to 0, then we factor or use the quadratic formula to solve for the variable. The same process can be applied to solving second-degree trig equations. Example, solve the following. So we have a algebraic equation, x squared minus x equals 0. We would factor out the common factor of x to get x times x minus 1 equals 0. Then we look at when each factor is equal to 0. So x equals 0 when x equals 0, and x minus 1 equals 0 when, if we add 1, when x equals 1. So our two solutions would be x equals to 0 and x equals 1. Let's do that same process for a trig function. We have cos squared theta minus cos theta equals 0. for a domain of 0 degrees is less than or equal to theta is less than or equal to 360 degrees. So 1 positive full rotation. And a note here, for any trig function, if you have the trig function squared and then theta, that's equivalent to brackets, the trig function, and then outside the brackets squared. So our common factor here would be cos theta. We factor that out, and we get cos theta times cos theta minus 1 equals to 0. Then we look at each factor and when that's equal to 0. Cos theta equals to 0 and cos theta minus 1 equals to 0. Add 1 on this one, we get cos theta equals to 1. Now we want to think about our unit circle and when cos theta is equal to 0 and then when cos theta is equal to 1. Let's draw our unit circle. Recall that for the unit circle, cos theta is the x value. So we have cos theta equals to 0, which means on the unit circle, we are looking for when x equals to 0, and cos theta equals to 1. So on the unit circle, when x equals 1. When does x equal to 0 on the unit circle? There's 2 points. We have the y-intercept of 0, positive 1. What's the angle measure at that point? It is 90 degrees. Then we also have x equals to 0 at the other y-intercept, which is 0, negative 1. What's the angle measure in degrees at that point? It is 270 degrees. Now, when is cos theta equal to 1? That would be when x equals 1 on the unit circle. Where is x equal to 1 on the unit circle? That would be x is 1, y is 0. What angle measure do we have for that point? First, we would have 0 degrees. And then if we do a full rotation, we would also have 360 degrees. And our domain is theta is greater than or equal to 0 and less than or equal to 360. So those points, 0 and 360, are included in our domain here. So our solutions then, when cos theta equals 0, we have theta equals 90 degrees and 270 degrees. And then when cos theta equals 1, that is when theta equals 0 degrees and 360 degrees. Factor each of the following expressions. So we're just factoring, we're not solving. Sine x plus 2 sine x cos x. We have a common factor of sine x. We factor that out. We're left with sine x divided by sine x is 1, plus 2 sine x cos x divided by sine x would be 2 cos x. Tan squared theta minus 9. This is a difference of squares. How do we know it's a difference of squares? The first term is a perfect square, the last term is a perfect square, and we have a minus between them, which is difference. To factor a difference of squares, we take the square root of the first term, which would be tan theta. That goes at the beginning of each of our two binomials. The square root of the second term, square root of 9 is 3, goes at the end of each of our binomials. One of them gets a plus, one of them gets a minus. And then secant squared theta minus secant theta minus 12. Think of this like x squared minus x minus 12. It's a basic trinomial. We want two numbers that multiply to negative 12 and add to negative 1. That would be negative 4 and 3. So then it would factor to x minus 4 and x plus 3. And then we replace the x's with secant. So secant theta minus 4 and secant theta plus 3. For solving trigonometric equations, state your answer as an exact value unless otherwise specified, and always use an algebraic approach unless otherwise specified. Example, solve sine x times tan x equals 2 tan x for the domain 0 is less than or equal to theta is less than or equal to 2 pi. Let's move everything to one side. We have sine x tan x minus 2 tan x equals 0. We have a common factor of tan x, factor that out. Tan x times, the first term would become sine x, the second term would become 2, and then is equal to 0. We want to look at each factor and when it's equal to 0. So tan x equals to 0, and sine x minus 2 equals to 0. Add 2 to both sides. We get sine x equals 2. Sine x equals to 2 is not possible. Think about the unit circle. The biggest value we ever have for sine x or for cos x is 1, and the smallest value we ever have is negative 1. Any other values of sine x or cos x are going to be greater than or equal to negative 1 or less than or equal to 1. So this is not possible. Because negative 1 is less than or equal to sine x, and cos x, which is less than or equal to positive 1. So we need to figure out when tan x is equal to 0. Tan x equals opposite over adjacent. On the unit circle, this is the y value over the x value. When is this equal to 0? It would only be when y equals to 0. So what we really want to look for on the unit circle is when is y equal to 0. Y is equal to 0 at our x-intercepts, which are at x equals 1, y equals 0. And that has an angle measure of 0 radians. And then if we go all the way around, it has an angle measure of 2 pi radians. Y is also equal to 0 at the other x-intercept, which is negative 1, 0. And that has an angle measure of pi radians. And if we were to go all the way around again on that one, that would bring us to 3 pi radians, which is outside of our range. We can only go up to 2 pi, including 2 pi. So we have 3 solutions, 0, pi, and 2 pi. X equals 0, pi, and 2 pi. Part B, write the general solution. Notice that our points are pi away from each other. So we don't have to write 2 separate equations. We can just write 1. We would have x equals, our smallest non-negative angle is 0 radians, so we can write 0 plus pi n, where n is an element of the integers. But we can simplify that. Instead of writing 0 plus, because really that doesn't do anything, we can just write x equals pi n, where n is an element of I. Or we could also write it, because technically pi is our smallest positive angle, So we can write it as pi plus pi n, where n is an element of the integers. Any of those three would be correct. For the following, give solutions as exact values where possible. Otherwise, give approximate measures to the nearest thousandth of a degree. A. If cos squared x minus 1 equals 0, solve for x where 0 degrees is less than or equal to x is less than 360 degrees. So notice that here we have 360 degrees is not included in the domain. Let's factor cos squared x minus 1. That's a difference of squares. So the first term in each binomial would be the square root of cos squared x, which is cos x. And then the last term would be the square root of 1, which is 1. One factor with a positive, one factor with a negative, and then equal to 0. We look at each factor when it's equal to 0. Cos x plus 1 equals 0. When minus 1, cos x is negative 1. And then cos x minus 1 equals 0. Add 1, cos x equals 1. So we want to know when is cos x equal to negative 1 and when is cos x equal to 1. And remember that cos x is the x value of points on the unit circle. Draw our unit circle. When is the x value equal to 1? Right here, x is 1, y is 0, and that's at an angle of 0 degrees. And then if we went around again, it'd be 360, but 360 is not included here, so just 0 degrees. And then when is cos x equal to negative 1? That would be here when we're at negative 1, 0, and that is at 180 degrees. So we have x equals 180 degrees for this solution, and x equals 0 degrees here. Part B, determine the general solution for cos squared x minus 1 equals 0, where the domain is all real numbers measured in degrees. So this is very similar to the question at the bottom of the last page. Our two different solutions are 180 degrees away from each other, so we can write them as one solution. If we write x equals, and then there's different ways to write it. We could write 0 degrees plus 180 degrees n, where n is an element of the integers. Or we could write x equals, leave out the 0 plus, and just write 180 degrees n, where n is an element of the integers. Or we could also write the smallest positive solution is 180 degrees plus 180 degrees n, where n is an element of the integers. Any of those would be correct general solutions for this question. Solve for theta. Cos squared theta minus cos theta minus 2 equals 0 for a domain of 0 degrees less than or equal to theta less than 360. Again, note that 360 degrees is not included. We can think of this as x squared minus x minus 2 equals 0. It's a basic trinomial. We want two numbers that multiply to -2 and add to -1. That would be -2 and 1. So we get x minus 2x plus 1 equals to 0 as our factored form. And then we change the x's back to cos. We have cos theta minus 2 cos theta plus 1 equals 0. Look at when each factor is equal to 0. Cos theta minus 2 equals 0. Add 2. We have cos theta equals 2. But remember we said the highest value for cos and sine is 1. So this is not possible. This is not possible. Since cos theta is greater than or equal to -1 and less than or equal to 1. Then our other factor, cos theta plus 1 equals 0. Subtract 1, we get cos theta equals -1. Remember that cos theta is the x value of points on the unit circle. So we're really looking for on the unit circle when is x equal to -1. Draw our unit circle. The x value is -1 here at the point -1, 0, which has an angle measure in degrees of 180 degrees between 0 and 360. So our only solution in this domain is theta equals 180 degrees. Determine the general solution to 2 sine squared x minus 1 equals 0. I can't factor this equation because 2 is not a perfect square, so then we don't have a difference of squares, and there's no common factor. So instead I'm going to isolate the x by adding 1 to start. We get 2 sine squared x equals 1. Divide by 2. Sine squared x equals 1/2. Square root both sides. We get sine x equals the positive negative square root of 1/2. Again, plus minus because we don't know if sine x started as a positive, got squared and is still a positive, or started as a negative, got squared and then became a positive. So we have to look at both possibilities. Then we can simplify this. Sine x equals plus minus 1 over square root 2. And we can rationalize the denominator. Times by root 2, top and bottom. We get sine x equals plus minus root 2 over the whole number 2. Which of our special triangles is this side measure from? It is from the 45-90 triangle, or in radians, the pi over 4, pi over 4, pi over 2 triangle. Let's draw our unit circle. Looking at the cast rule, we have sine is positive and negative. So actually our solutions are going to be in all 4 quadrants. And then our reference angle is 45 or pi over 4. So our terminal arms are halfway between the 2 axes in each of our quadrants. So our solutions, we would have one at 45 degrees, The next one would be 180 minus 45 degrees, which is 135 degrees. Then we'd have 180 plus 45 degrees, which is 225 degrees. And then our fourth one in one positive rotation would be 360 minus 45 degrees, which is 315 degrees. I'm going to draw another diagram here. If you look at the distance between these two angles, you should notice that this is 90 degrees. And then if you look at the next angle, this is also 90 degrees between those two angles. And the distance between these two angles is 90 degrees. And the distance between these two angles is 90 degrees. That's because our reference angle is 45 degrees. So this is 45 degrees, and this is 45 degrees, which adds to 90. And because 45 is half of 90, then this side is also 45, and this side is also 45. Those add to 90. This is 45. This is 45. Those add to 90. This is 45, and this is 45, and those add to 90. Then to write a general solution in degrees, because this question doesn't specify, so in degrees, our smallest positive angle is 45 degrees, and then our next angle is 90 degrees bigger than that, so plus 90n, where n is an element of the integers. To write this in radians, (45 degrees is pi over 4, so x equals pi over 4, plus 90 degrees is pi over 2, so pi over 2n, where n is an element of the integers. There's our general solutions in both degrees and radians for this question. That brings us to the end of the Chapter 4 notes.